Hey, I think we are live now, and I need to tell the folks on Discord that we're live. Should post a link to it in the Discord link in the live chat too. Okay, I've got that. How in the heck do I get the link? Cool. All right, I got that. Oh, I should probably pull up the chat. Oh, yeah, I'll post the Discord link. Give me 1 minute here. Okay, there's the Discord link in the chat. And then most people watch from YouTube, it seems, not the Zoom thing that I set up. Although some people do drop messages in the Zoom chat as well. And I just kind of post them up on my screen over here. And I did do some pre-work again this time. I will show that so you guys actually have something to look at while waiting. Nope, hold on. So it's a little bit similar to it's so we leveraged orchestration in a couple of other problems. So this is actually we covered orchestration implementation a little bit in the workflow video. The workflow, what the heck did I call it? Workflow automation, I think was the name of the video. We did kind of cover orchestration before over there. But orchestration on its own is actually a Google interview question. The full prompt that I've basically received is this one: design a service to execute several tasks consisting of 1 million or more steps each. And this is the rough design I'm going to kind of be going over on it. It's a little bit easier. There's not as many variations of it that I've come up with as previous problems. So it's a little bit less exciting, a little bit more straightforward, but still should be a fun problem. Yeah. Oh, and let's pull that back up there. Okay, I think we're probably good to go ahead and get started. All right, I'm actually going to, I don't know, I'll just move this off screen. It was a little bit of pre-work I did on the problem. I guess I can clear this off. Okay, so today we're going to go over the design for implementing orchestration. This is from a real Google interview question that somebody had showed me. I didn't get a lot of clarification for it. It was somebody else that went through the interview a good couple of months back. The exact prompt that the fullest extent of the details on this problem that I received was roughly this. Design a service to execute several tasks consisting of 1 million or more steps each. So they did not actually, the Google prompt was not actually design orchestration, it was design this, but that is roughly what orchestration is. It's to execute a task that involves several steps. Each step could have faults and require retries. It's basically running a workflow. So again, it's from a real interview question. Some great resources for learning about orchestration, how to implement it are here. So Netflix Conductor is one open source implementation of orchestration. It has phenomenal documentation. Netflix creates a lot of really great stuff. And Conductor is one example. In their documentation, they might actually eventually support AWS step functions language. I think it was like ASL is the name of it. Of the orchestration solutions out there, I think the most well-known is AWS step functions. There's another AWS orchestration solution. It's SWF, Simple Workflow Service. There's a couple of other open source ones out there, but I think this one's the most well-known. And in terms of just general components that people usually work on top of, I think AWS Step Functions is the most well-known example. And then Netflix Conductor might even support the language you can, it's maybe going to be in their roadmap to support the language that is used for making these AWS Step Functions, which would be really sweet. Yeah, so that's so we're going to implement orchestration. Any questions before we try and dive into the problem today? Okay. I think orchestration can be a little bit confusing of a component. I did have a previous problem that did kind of use it within a context. We did kind of go into the white box, black box implementation details. It was workflow automation. But we're going back over it because it's on its own. It's apparently actually an interview question Google asks. Anyways, so I also looked into task queues like Celery, because those can actually kind of be viewed as a subcomponent. So we can go ahead and start diagramming a bit. Is that you're of course going to have some workers. You're going to want to have some workers that are processing these tasks, that are doing whatever the steps are. And then the steps are going to depend on each other. And so you're going to need to have some kind of directed acyclic graph of these steps that depend on each other. Okay, somebody does have a question. Yeah, I guess this is enough information to chew on for implementation while we go through a couple of questions. Similarity between orchestration and, okay, so a job scheduler is when you're just running like one step. It's when you just have like one step. So if you have a bunch of jobs that depend on each other, that's like orchestration. So in fact, that's even, so you can think of, I think you can even set up AWS step functions kind of like lambdas that depend on each other. So a single AWS step is basically the same thing as an AWS Lambda function. So if you have jobs that depend on each other and form a series of like steps, so I can go ahead and draw this out even. So we'll have like a step over here. Let me fix the sloppiness. That bothers me so much. So you got two steps over here, and then you got a third step over here. It depends on both of them. And you got a step that depends on that. So each of these four circles individually is a job from like a job scheduler. And then if you have them depend on each other like that, I never had these circles shaking like that. I don't know if you guys are able to see it. I have no idea what's going on. That's like a weird new bug I've never had before. So anyways, one step is a job from like a job scheduler, and together all four of them as individual steps form a like workflow. And orchestration is we're running a workflow. And then in broader system design, you might have heard of orchestration versus choreography. And so it's just two different ways of handling a series of calls and steps that need to be handled and responding to a request from a client. Is that you have this like request come in, and then you call service A, call service B. Depending on the output of those two services, you might call service C or do some kind of processing, and then some kind of other operation D happens. It's a series of steps. Each individual one might be like a job with its own output. And then another great question, are the tasks sequential or can they be parallelized? I'm assuming they can be parallelized. I think it would be fair to generalize this so that the tasks form, well, so you have another important clarification. So you have tasks forming that are of millions of steps each, and I'm assuming that each task is fully independent. And then the steps could be parallelized though. So that the tasks are like just completely independent runs of, so in normal orchestration terms, you have like a workflow that you run through the orchestration, and a workflow consists of steps. And so I'm treating each task as like an independent instance of a workflow. So we can clarify this further in the requirements is that tasks are fully independent of each other. And then steps can depend on each other, and some can be parallelized, or dependent upon each other. So these will form a DAG, but the tasks don't form any kind of relationship between each other. They're fully independent is my assumption. If they were dependent on each other, then it would just be a DAG of DAGs. And so then it would just be one, instead of being a couple of independent DAGs, it would just be one big gigantic DAG. And then that would make the problem a little bit more boring, possibly. Yeah, good question. Okay, so we've gone over that. Feel free to ask any other further questions as we're going along, but that is my assumption. I'm also going to assume that it takes, we're going to say it takes 1 minute to run a step. And like I said, we have millions of steps. I'm going to try and do some scale numbers here. I've been slacking on that for a lot of problems over the last month or so. I'd really like to do some machine count estimates today, though, since this should be a simpler problem. Maybe even some latency problems if we have time for it. We'll see. And there was another thing. So I'm going to try and remove that from the scope is the way that the tasks are loaded in. So that the DSL is like how you would load in the relationship between the steps. And so ASL is an example of such a DSL for describing the relationship between the steps. That's why I thought that was really cool that Netflix Conductor would be implementing ASLs. That currently it's a very proprietary language just used purely within AWS land. And then having it applied to this open source tool, that would be very cool. So the DSL is an example of one such DSL would be Amazon Steps language is what it's called. And they even, I think AWS Steps language itself might even be open source, but AWS Step functions, things that run this DSL, are very much closed sourced. Yeah. Okay, we'll keep moving on. So we have these workers, and then like you said, it's going to have to get in there somehow. So there's kind of like two steps to this is like the describing the steps and their relationship to each other. And then the second is actually invoking it and kicking off the first task. And then there's so we're gonna have upstream client. So it's I said browser, but it's upstream client. So like an upstream service could kick off a task. So it would be kicking off a task. I think I got another question in the chat. We're going to try and make a little bit of progress before I get back to it. So you'll be kicking off a task, and I think we should have a backend service. So this would be the scheduler service. It's going to receive your request to kick something off. And there's of course a second, there's of course a different thing entirely, which is upstream client describing. And this would be the DSL you were talking about. And so this would be like a one-off thing where you describe a workflow, and that would be like an engineer would be doing that, while this would be an automated process of kicking off a task. So this one's automated, this one would not. This would be like an engineer specifying a schema or something. And so we're not going to focus on that. We're going to leave that one out of scope. Possibly we're going to kind of describe it a little bit, but what I want to focus on in the problem is kicking off tasks seems to be kind of it seems like this is where the focus of it would be is, hey, here's the task ID. And then this thing would have the schema already ingested and serialized into some kind of thing that stores it. You might be thinking of a graph database. So we're going to need some kind of DAG data store. And so when you have a DAG, you might think like, oh, graph database. And I think we went over this before, but you only need those if you do traversals of the graph. And in this particular case, we're not going to be doing like BFS style traversals. It would just be like a depth of like 1. But if you're doing like recursive calls for traversing the DAG, that's when it'll be necessary. But I think the traversals are only going to be at like a depth of like 1. So you'd not actually really need a graph database. You can just get away with something like DynamoDB or something. So you would need the schema definition, and you would also need an instance of the task that's being run. So there's like the meta data of like the workflow, and then there's an instance of the workflow. And when I'm saying workflow, that's a task from the prompt. So you would have this. So you're going to pass in a task ID for what you want to run. And the font looks ugly right now. So you pass in a task ID. And then the scheduler service is going to go ahead and pull off the first steps for that one. And it's going to want to pass those over to the workers. And now this communication is where we're going to get interesting. That's kind of like the first piece of the meat for how we're going to, the diagramming work. The first piece of meat for the diagramming work in this problem is it's like a sub part of orchestration is like a task queue, like celery. Okay, and then, we didn't actually have any further questions in the chat, so I can keep going along here. Okay, so I said here, there's two different kind of like pieces to it. There's like, you can kind of break off a sub piece of this as the task queue, is that, so you've got these workers. And I mean, I guess you could maybe just talk to them directly, but so you can either push the tasks straight onto the workers, or the workers could pull work off of a queue. So another approach could be that you just decouple these from each other by adding in a broker. But I guess we could even call that two different approaches. One is the push models, where you push directly to. So we'll go ahead and do approach one is push model. And then you've got approach two, which is workers pull tasks off the brokers. This one doesn't have the broker. You're just pushing straight to the workers. So that would be, go like this. You're doing a call and then you get a response back. And so if you don't have a broker, that would mean that you'd have to do the retry logic directly on the scheduler, which could be a hassle. And so there's that, pushing steps to the workers as opposed to approach 2, which is that you have workers pull steps off broker. And this is kind of how task queues like Celery work, is that it actually is ambiguous to, it's what is it, agnostic to the broker you can use. Like if you go on Celery's documentation, your broker can be RabbitMQ, it can be Kafka. They don't really care, but it actually has a broker in the implementation. It's in the documentation of Celery's, that it's like, hey, pick your broker, pick your result store. So you're going to have it like taking stuff off of the broker, and then it's going to run whatever processing work it needs to, and then it has results, and those results are going to go somewhere. So we talked before about how you have like the metadata of describing a workflow, like the schema of a workflow, and then you're also going to have like a workflow instance. So it's like a DAG. You also have like a DAG instance. And the results could maybe be stored directly on that. And so that makes sense in the context of orchestration. But when you're just talking about a task queue on its own, like Celery, which doesn't do orchestration, it just actually had a results store separately. But like tracking the progress through, like, so when you generalize the approach, you could, roll your own task queue within the orchestration thing you're implementing instead of trying to build it. You can either try and like build orchestration, I feel, on top of a task queue, or you can just go ahead and roll the whole thing from scratch, and then you might be able to use a couple fewer components if you do that. So one is, so if you're doing a task queue like Celery has, it requires a results store. And so when it's done doing that, it writes the output to that. And then, so what you've got is, that is a, whoops, I want to move this over like that. There we go. And so this is what a task queue has. So if you're just building on top of a task queue, you can build on top of this. But if you roll it from scratch, you can probably combine these two things. So I'll get into that in a second. I think we do actually have some questions now. I'll zoom out while going through those. Okay. What other task queue workers can you use instead of Celery? Why choose Celery over any others? Well, I was just using it as one example. I haven't dug into a couple of others. I know there's other ones out there. I haven't looked at their documentation as much. I'm just more, I think that was just the most prominent task queue that's out there. So why I picked that one, it's just the arbitrary one that I picked. It's the most well-known one in the task queue space. And then you don't actually have to use a task queue. You can just roll it from scratch. And so I'll do that in the next approach. Is so this one is building on top of a task queue. And then you can, of course, not actually build on top of a task queue. And then you could probably combine these two data stores. Okay, there is another question. Yeah, all right. Yeah, I should probably get into the schemas a little bit. Yeah. Yeah, let's maybe go into the schemas a little bit, and then we can go into approach 3, which is where we just go ahead and combine these two things. So again, to kind of recap what process we've got so far, you want to kick off a task ID. The scheduler is going to take the first couple of tasks. You might even want to decouple these things because there might be, well, I don't know, if it does a partial failure where there's an issue before it returns successfully to the client, then the client would just try and kick off another task ID. That could have the issue that you might get it onto the broker before you return all the way to the client, and then you would have two tasks running through the broker at once, which would in the first one would of course just be doing work that's just kind of getting thrown away because the client's not aware of it. So you should probably maybe like stick a broker in front of it and just spin up they have a task ID you want, and you're going to return a task instance ID. You want to pass back a task instance ID. And we got a nice partial failure scenario, which is handling what if it sticks the thing on the broker, sticks something into one of the data stores before it returns to the client, and then it fails part of the way through. And then we've got this random runaway task that is just doing work nobody's actually going to look at. And so we might want to throw in a broker here, and I can get to that later on. But yeah, something to keep in mind is nice partial failure scenario there. Okay, let's go ahead and dig into the schema though. So we've got this, like I said, it's going to have, you're going to have these like parent tasks. Let's go ahead and do this. So let's talk about the schema first. Is so you'd have a specific task that you're trying to describe, say that, and there'll be a certain step. Say it's step number 567,000. And then you of course need to capture the relationship between these steps. Okay, so each step can have a certain number of, it can have multiple parents, and it can have multiple children. Okay. So then that is a NM relationship between the steps. So then we're also going to need to have a join table we're going to need to have a join table. So it's actually going to require two separate tables here, but it's only describing the, it's just the schema, or like the DAG of the instances that you're going to run. You're going to run a couple of instances of a task. So we're probably going to be able to get away with a PostgreSQL database, and it's just fine that we're not going to need to, we probably won't need to denormalize it. If we did want to denormalize it, we could probably just have a list of child steps, or we could have a list. Yeah, we wouldn't want to have a list of parent steps. We could probably go ahead and have the list of children in the step if we were going to denormalize. But that would still, yeah, that would still probably result in some expensive queries. It would probably be a bad idea to try to denormalize it at all. Yeah, this would probably get really nasty if you had to try and denormalize it into a NoSQL database. But I'm pretty confident we'd be able to get away with keeping it in PostgreSQL. Anyways, parent step ID. We'll say that this one has a parent of we'll just subtract 100 from it. So we'll say that the parent is 5, 6, 900. And then the child step is 567,000. Okay. And so for the given parent step ID, there'll be a couple of records that have this thing the same, and then value would be different there. So the primary key of the join table is, of course, the combination of both of these foreign keys. It's a PostgreSQL database. And do we need anything else on this? I think that should be enough to specify it. I see we've got a couple more questions in the chat. Maybe I screwed something up. Let's see. Okay. Well, so Lambda functions are like a job runner. You could use Lambda functions as like the workers. In fact, so within Amazon, you've got AWS step functions, then you've got this thing called herd. So there's this thing called herd, you've got AWS step functions. And then herd has a couple of different things. There's like this thing called like a SIL function. And this is analogous to Lambda function plus a API call or something. And so step functions, like you can build them on top of Lambda functions. So each step is kind of like a Lambda function. But I don't know if like I don't know if a Lambda function would be set up in a way to retry, and it looks like with a task queue, it would just totally be, it has a lot more retry handling like set up with how this looks. Like if a worker picks it up and then it flops on trying to handle it, so if you're using like RabbitMQ, for example, where it does internal failure handling, if a worker picks up a task and then it dies while trying to execute it, then RabbitMQ would still have it on the queue and it'd get picked up by a different worker. With the volume of tasks we're handling, though, we would probably be doing a stream, though. And so with a stream, you don't do the internal failure handling like that, which is a little bit different, but you can still do, I mean, you still got retries like very handleable with a stream, but I think AWS functions even have like this timeout thing on them. Like you can't run something for more than was it 30 seconds? I gotta look at that again. The workers here though are just kind of like EC2 instances. It's just like you've got a bunch of machines, a bunch of boxes set up. It's a little bit more bare metal than Lambda functions. And I think if you were asked to do this question in an interview setting, Google likes it when you roll stuff completely from scratch. Google likes it when you run stuff completely from scratch. So it's like if somebody tells you like in an interview, like, hey, implement a job runner or something, and you're like, oh, sure, let's just use Jenkins or let's just use AWS Lambda, then you're not actually rolling, you're not really solving it right. It would kind of be like analogous to how that would be analogous in a coding interview would be like if somebody tells you to implement some kind of problem that involves binary search, then in Python you just go import binary search and it does it all for you. So it's like you can't do that there. And so AWS Lambda functions in this context, I think would kind of be like using an unfair library with an encoding question. Good question though. I think in this, I brought up Celery as a reference for like how to tackle this problem. I like to say that my diagrams are not an answer key. They are my best effort at it, and so are Alex Shu's books. His books are great, but they're also not an answer key. Celery is really well-made stuff that people have been working on for years on end. And so I refer people to like some other references because it's like that's like way more thought out than whatever the heck I'm going to spin up within like, an hour. And like, I mean, I do research beforehand, of course, on these problems, but like, it still is not going to be as much research as was put into building Celery. So that's kind of why that's there, but I don't know if you can actually go ahead and build on top of Celery in a real systems design interview where you're asked a question like this. Okay, that was maybe a little bit drawn out. There's a couple more questions in the chat. I missed which type of broker you're using. I'm going with Kafka. I usually go with Kafka for just about everything because you can't get what's it called? Back pressure. So with RabbitMQ for like message queues, you can get back pressure, while with a stream like Kafka, you can't really get back pressure. So that's why I'm going to use, I think you should use Kafka here. And then I didn't really explain the mechanism for how the worker is going to avoid picking up the same exact work as each other. I should probably think that out a bit more. I don't know. Maybe RabbitMQ would be fine here. Maybe RabbitMQ would be fine. Yeah, you know what? Okay, I'm changing my mind. I'm going with RabbitMQ. And let's maybe crack some scale numbers really quick. Okay, 1 minute to run a step. I already did a little bit of math. I know you guys hate it when I do the math during a stream, but we're gonna try and do this really quick. So we've got we're gonna say that we've got 5 tasks that we want to run, and they are 2 million steps each. That's 10 million steps that we want to run. And we're going to assume that it is 8 threads per CPU. So on an EC2 instance, they do use those beefier CPUs like AMD Threadripper or whatever, which has like 64 cores. But you're sharing that you're sharing that EC2 like CPU with like a bunch of other people actually. And so they only actually give you like 8 threads. And it's like vCPUs is I think what it calls it. So they're only actually giving you like 8 threads, even when you order like an extra large. So you have an EC2 extra large instance, you're actually only getting like 8 threads, which is crazy. But we're going to say each machine can run 8 things at a time. So we've got 10 million steps that we want to run. So how many steps, how many minutes would that be of running stuff on a single machine? So on a single machine, fully parallelized, that would be like 10 million divided by 8. And we're going to round that up to around 8 to 10. So that's going to come out to 1 million steps per machine. And so if you've only got one machine that you're going to run, that would mean that it's 1 million minutes of to run the 5 tasks. And then that would be how many hours is that? I think that was like 16,000 hours, 16,670-ish hours. And then I think it was like 694 days. And so it would take us 2 years to run these 5 tasks that have 2 million steps each. I don't think that's reasonable. So I'd specify, you should clarify with the interviewer, hey, how quickly do you want these 5 tasks to get done? Let's say that we want to get them all done in 1 day. You have 1 day to execute all 5 of these tasks. I mean, there's issues with like dependencies. So like how much throughput can you really get? Let's say that they're ridiculously parallelizable and that these DAGs are like, they have a width of like a few hundred or something. And so then you can actually get some proper throughput and really parallelize it. And so let's say we want to get everything done in 1 day. If we want to get 5 tasks done per day, if we want to get 5 tasks done per day, we need 694 machines. So we're going to have 694 worker machines. That's what we're going to be doing. So 694 worker machines, and they're going to be handling 8 tasks. So how many steps are going to be going down this broker at a time? How many steps going down the broker at a time? I'm trying to figure out if we need RabbitMQ or Kafka right now. That's why I'm doing all this math. I'm not just trying to show off my math skills. How many steps getting thrown down the broker at a time? So we have 694 machines, 8 cores each. They're going to be running 8 tasks at a time. They take a minute each. So it would be 694 times 8 steps per minute. So each task can be taking a minute to run. So then that would be 694 times 8 per minute. And we want it per second. So what is 694 times 8 though? I'm cheating, I'm using a calculator. 5552 steps per minute. And then per second, that would be, we divide that by 60. So that should be coming out to around 100. It's around 100 steps per second. I think RabbitMQ can handle that. So we're going to stick with RabbitMQ here. And in fact, having 694 workers for this, I think it feels excessive. It feels excessive. I don't really feel like we'd actually have this horde of like 700 boxes running this setup. It just feels weird to have 5 tasks running on 700 machines. That just feels weird. So I feel like the real scale would actually be even smaller. And so RabbitMQ should be able to handle our traffic volume pretty comfortably, I think. You can also shard RabbitMQ. You could have multiple RabbitMQ brokers set up. And so then you can just scale it like that. But we're going to be doing point to point. And so I like RabbitMQ here. This is one of the only instances where I like RabbitMQ for a design. Otherwise, I usually hate having RabbitMQ on my stuff. Yeah, we're going to use RabbitMQ though. Okay, there was other questions. If in-memory is used, how do you handle dependent tasks executing out of order? Well, so you should not actually have dependent tasks executing out of order with how you would be fetching it. You would fetch the first layer of the steps, and then you would actually be using the DAG instance, and you'd be tracking it in a way that would prevent. We didn't finish the schema there for the second part. Is you would track a bunch of records that are like this. This one would not be PostgreSQL. This one has a higher write volume. This thing's going to be read heavy. You're going to have a very small amount of data. You might need to scale it up with read replicas, but you can definitely do PostgreSQL on this one. You can definitely use PostgreSQL over here for the DAG data store. It's such low write volume, but over here you might want to go with like, DynamoDB with strong read consistency, it's probably going to work fine. I don't know if eventual consistency is going to be good for a use case. I mean, it wouldn't really break anything if you did eventual consistency, but then you might get stuff that's getting rerun, which I mean is not the end of the world. I mean, you can probably get away with eventual consistency. It just seems cleaner if you get strong read consistency. I don't want to get hung up on that. It's one of the less interesting aspects of this design. And then you would have like the step ID, So this is just the metadata schema, and then you would have an instance, and then you would have a instance of, it's the task instance ID. So like you make instances of a task, and then each step together, all this should form a unique identifier. So all three of these together would form the primary key. And so I should maybe mark that. And so we would say this is instance 4 of it. We've only run this whole workflow 4 times somehow. Yeah, okay. We should maybe talk about the partitioning key and the sort key, which would, right. Okay, so you would pick out the partitioning key to make these, you're going to do key range queries here. You're going to do key range queries, and I think you would want to have the task ID and the task instance ID to hopefully be on the same partition. So let's say we're doing 5 tasks per day. And then, so this is going to be part of the partition key. And then that should still have enough granularity that I think you wouldn't have a task ID paired with a task instance ID spread across multiple machines. Because you're probably going to end up having, like, let's say 4,000 over the course of like a year or something of running a specific workflow. So this is going to be partitioning key. This one is also going to be part of the partitioning key. And so then this is going to be the sort key. And that would allow your key range queries to not result in a scatter gather, and that would be more efficient. And so you're going to retrieve, that didn't actually answer your question, I'm sorry. So you would have, you would also need whether it's completed or not. That's another crucial piece with being able to get the key range query for answering your question. I'm trying to get the key range query that would answer your question here. That's why I'm going off on this tangent right now. I'm trying to get the show you what the key range query is. So you have a status of complete, or it might be pending, or it might be work in progress, as in it's currently executing. And so then you would retrieve for a certain step ID, when a certain parent step ID completes, you can fetch all of its child steps. And then for each child step, look at whether all of its parents have completed execution for the current task instance. That would be what, that's what we would be doing here. And that does sound a little bit, okay, let me write that out so that I can think through this a bit. So every time that a step completes, check whether all of its children can execute. Would be due to all parents being in a state of complete. Now that does look a little bit more like a traversal. I don't think you do actually need to do a graph database. Graph database is when you need like multiple layers to it and you're doing something more of like a BFS style relationship. But I mean, it does look like a little bit more sophisticated of a key range query. And you might even want to do So it's like, this is like one query, and then you can like, that would result in a bunch of child steps. Then for each child step, you're also going to be doing a key range query. So you might even want to like have a broker between these two steps, and you'd fan out a bunch of messages of the child step IDs. That could maybe make sense. Yeah. And I got some other questions I'm going to answer in the chat here. Okay, should we add a status of a task to the schema? Well, so we have the steps. We have the steps status, the task itself. So you would get to the last steps of the task. I guess you could have you'd have something that looks like you have your thing, and then you could have a complete step. You could have a completion step, and it's just like a dummy node kind of, and you just kind of like formalize you'd have a step, just one step at the end, even if there's like a bunch of parallel steps, and then you just have this, it doesn't actually do any computing, it's just the final step. And once all of its parents are in a complete status, you can just go ahead and go through all of them, and it's like, oh, okay, they're all complete. Now run the final step, and it's just a dummy step. It doesn't actually do any compute work, and then it goes to complete. And then you can just kind of check that step, and then you would have to have a separate table or anything for checking the status overall. But I think that would allow us to kind of do something similar. And you can do something also for the top of it. You can do a first step. And then, yeah, that could kind of simplify things. I see where you're going with that. I do see where you're going with that. I don't think you actually do want to add a whole extra table to the mix of things. Good call out. I don't think we want to add a whole extra table though. Elaborate on the semantics of task instance ID. Well, so somebody asked earlier how you would specify the dependencies of these steps upon each other. So it's a task similar to the concept of a workflow from normal orchestration. And so you first need to say like what you would have an interaction where the client actually specifies the dependency of the steps between each other, and then they would kick off instances of this workflow. So you describe all the steps, and then you make an instance of executing a series of steps. Then I got another question in the chat. For the schema, how are we querying from DB and ensuring we are doing the tasks in the right order? I think I was just answering that, and yeah. So let me maybe go ahead and dig into how this would look. And I had said earlier, you can probably combine these two data stores. We can maybe go ahead and do that in this third approach. I'm just going to do them both. We're going to go through decoupling what's going on here, and also combine these two data stores in this case. So we're going to delete this box. We're not going to build on top of a thing anymore. So you've got this schema that you described. I guess we can go ahead and make we'll call it the description service. So at some point, he maybe uploaded a file or something, and that data made its way into the DAG, the metadata store. And then you got this task ID that you want to kick off. And so we have 2 query steps, and you want to gather child steps, and then you want to check whether the child step is actually able to execute. This is, I feel like I'm doing something really stupid here, but whatever. So you can gather all the steps for, so when you're first kicking off the task ID, that would be the first step. You got this first step. It's like, it's thinking, oh, okay, this is a task ID. We're going to kick off one. So the step that I'm looking up is the first step for a task. And so that could even indicate that record in a special way in the metadata store for when you're looking up, it would be like null. And you know what? I think you would maybe want to also have the task ID for these pairs of this relationship between the child steps and the parent steps. You don't need it for, so it is just a NM like join table between like 2 entities in like an ER diagram. But I think it would actually kind of make sense to have the task ID in there too. And then this would make it really easy to look up what that first step is. I think that kind of makes sense. And so you're going to look up the first step, or if some other task step completed, you're able to look up all the other child steps of that. So you're either looking up the child steps of the first step, or you're looking up the child steps of some task that just completed, look them up, and then we're going to pass them over to this other thing that's going to check whether it's actually ready for execution, whether you can actually pass it on for the workers to go ahead and do some work with it. Just going to have this. We're going to move that over there. Got this. So I'm like splitting the scheduler service. I'm going to load all these steps that we might be able to execute. And then we've got this other one, and this one is going to look up all of the parents for, so it's going to put a bunch of steps onto this broker. And then this broker, for each of those, it's first going to make a call to this one to get all of its parents. And then it's going to look up the status of all those parent steps. There's probably a cleaner way to do that, but now I'm really curious how the heck conductor does it. Okay, let's make this look a little bit more clean. So we'll put a bunch of steps onto here to check whether they can actually execute. This one pulls one off. Hey, what are the parents for it? And then look for all those parents. Are they complete? If not, then it'll just ignore that message. If they are complete, go ahead and pop it onto the broker, and you can go ahead and try to execute it. And now we can also go ahead and combine these 2 data stores. So do we really need to have the results store? This was just going to be like S3 or something up here. It was, you can just have it as S3. I'm just thinking of like an output file. When I was in college, I actually took a class on parallel computing, and I did stuff with like CUDA, and then we print out this like big text file, the results from a processing job. And I was just kind of thinking of that. But you could even maybe just have an object straight on the data store. You can actually have records of the records within a lot of databases can actually get pretty big. I think in in PostgreSQL, you could actually have a single record could be at least a couple of megabytes, maybe as high as like 200 megabytes, or even I think in Elasticsearch it was maybe even like a gigabyte or something. It was crazy how big you could make some of the records in a lot of data stores, but you can actually just go ahead and stick the result directly on here. And you could have it as just a blob, like a binary blob or a text blob or a JSON blob, but you just have some kind of large data blob like that. And so get rid of the results store. It's on there. And then you should go ahead and have separate attributes for status versus the result, even though the result will be null versus you know, output there. And so it looks like it have overlap with status, but that is the single responsibility principle. I don't think it's a good idea to try and reuse the result attribute to also be the status attribute and then doing like a null check for determining it. I don't like that. I think it violates the single responsibility principle. So we can go ahead and combine the data stores, just not that specific attribute. And so there we go. We've separated the two steps from this thing. We've combined the result data store. I've gone ahead and I said I wasn't going to do this, but I did provide some further details on this. I guess it is fair. How fair is it to just say that the EC2 instance takes the file and then does the parsing and sticks it directly on there? I think it is kind of fair. It is like a million. We're saying that there'd be like a million lines on the file. I don't want to get carried away with that though. You can just use an S3 bucket or something and then have a task runner do that. But the interesting aspect of this problem though, I think is in the steps, the dependent steps. Okay, let's move on to any other questions. I see another one in the chat. Could you briefly go over the difference between a DAG data store, DAG instance data store? So this one is the schema. This one just stores the dependence. This is like how the workflow looks. So you would specify a workflow that would look something like, say that this one is connected to all four of those, like that. And then we'll say that. This is what I was thinking of. So this is one workflow. So you have this. This is one relationship of a bunch of steps. And that is captured over here in the DAG data store. And then what you have in the DAG instance data store is that we've got two tasks running of this whole thing. So here's instance number one. Here's instance number two. And then in this first instance, we'll say that, hold on, this one is green, it's complete. This one is not complete. Say red. This one is complete. Now we're going to go over here. In this case, though, that one is not complete. That one's red. This one is also not complete. In fact, this one is, whoops, meant red. In fact, this one is just getting started. It only has one completed task over here. I have that one as green. That's really all that's really how far we've gotten into that task so far, is that we've only got one step complete, while over here we've got 1, 2, 3, 4 steps completed. So it's you've got multiple instances of a workflow going on. This one does not store any of those statuses. This one does store the status of each of the individual steps. You need to like copy this multiple times into the DAG instance store. Otherwise you can't put that information onto this. It just wouldn't work because it's these are like different objects. It's similar to having a class specification. So like in Java, you have like a class and you can have like static instance variables versus class instance variables. And so this is kind of like a static thing. This is like the class definition, or like in C++, you could say this is like the header file, while this is like an instance of a struct, or it could be like it's like the instance variables. This is like an instance of a class, while this is the class definition. That's what's going on here. You've got your definition of a class, and then you've got instances of a class. And this is like the status of each of the steps, the specific output for this instance of the step. Yeah. Okay. And this is for, I didn't fix the text. This is approach 3, and we're building it from scratch. Building from scratch. Okay, and I did go through the scale already. I'm going back through other things I wanted to cover today. I already did a machine count estimate for the workers, and it's 100 TPS going through RabbitMQ. Maybe you'd have 2 RabbitMQ instances or 5. You could chart it out in order to get proper scale over there. And then 100 TPS, like maybe you would need like maybe 2 to 3 machines over here on the scheduler service. You'd need anything upstream of there, you'd only need like 2 to 3 instances. For the DAG data store, how many do we need for the data stores? How many machines do we need for the data stores? So the DAG data store, I'd assume that we're going to have hundreds of instances per task. And so that means that we're not going to have to specify a lot of different tasks. So this one would depend on how often you're going to be finding a new task. This one is easier. We already have enough information to estimate this one. Is that we're making 5. We are making 5 tasks per day. And each of those tasks is going to have a million steps. We are running 10 million steps per day. So every single day, we're going to need 10 million records in this one. And then how big is the result going to be? So let's say that the result is going to be 1 kilobyte of output. 1 kilobyte of output per step. And so how much storage are we going to need for running it for like 5 years? So 1 kilobyte relative to the rest of it, that should be the biggest thing in here. That's so 1, 2, 3. It's like 4 ints. And an int is like 4 bytes. That's like 16 bytes versus 1,000 bytes. So it's going to be about 1,000 bytes per row, roughly. So 1 kilobyte per step, 10 million steps. So how much storage for 1 day? I'm going to do 10 million times 1 kilobyte. That would be 10,000 times 1 megabyte, or 10 times 1 gigabyte. So we're going to have about 10 gigabytes per day for 1 year. That would be 10 gigabytes times 365. That is 3,650 gigabytes per year, or about 3.5 terabytes. That's about the size of you can definitely fit 2 terabytes on a hard disk, particularly when it's at a data center. Probably want to make it redundant. So I mean, even if you can fit all of that on one hard disk, you're probably going to have it. You're probably going to make it replicated. So I'd say that you're probably going to need at least 3 hard disks for handling 1 year of storage. And so I'd say you wouldn't need more than, well, so like that's just purely for the sake of redundancy. I think you can actually get like 10 terabytes to a hard disk. Some you might be able to get 100. I don't know. I might have that wrong. I know you can get 2 terabytes. You know, we'll just stick with 2 terabytes to a hard disk. We'll say that the max storage you get on one hard disk is 2 terabytes. So then we would need at least 2 hard disks for handling that much storage. And then you want to replicate it at least twice. So we'll say that we want to have at least 2 extra copies of it. So then you would get 6 hard disks for handling that much. And then after 5 years, we're just going to multiply it by 5. We would, well, so we're going to do 3.5 terabytes times 5 is 15 plus 2.5, 17.5 terabytes. We'll replicate it 2 more times, so it comes out to roughly 60 terabytes. You can store 2 terabytes to a hard disk, so we're going to need 30 hard disks after 5 years. And I think you can have a couple of hard disks per machine. You can do a disk attached, network attached storage. Do a network attached storage. That's a trick. I mean, at absolute most, you're only going to need 30 machines there, and we already went over the number of machines we need for the workers, which is like 600 or 700. So let's just say 30 machines for storage. Let's say that we have 3 hard disks per machine. Yeah, okay. So we're not writing to, we'd have data from a couple of years ago stored on a machine that's also getting updated with data from the current year. So let's say 3 hard disks per machine. We'll say that we need 10 machines for storage, and we're going to say 3 hard disks per machine. Yeah, okay, that's fair. So we need 10 there, 600 to 700 workers, 2 to 3 machines on the scheduler service, maybe 2 to 3 over here. This one's only going to need a couple as well. Yeah, this one's going to be a lot smaller than that one. We're going to say that we're going to make a couple hundred copies. Oh, and then this is storing the results. This one doesn't store the result, and so that would also make it a lot smaller. You're hardly going to need any machines for this. Yeah, maybe bandwidth is going to be, no, we only have 100 TPS for the steps. So if we have 100 TPS, what is the bandwidth on this thing? So then what about for bandwidth? Is that going to be a bottleneck? So we have 100 TPS of steps, 1 kilobyte per step is going over this wire to right over to here. So then that is 100 kilobytes. It's going over the wire, or about 0.1 megabytes. It's very different than a megabit, and you only get about 1 gigabit per second. So 0.8 megabits per second. So no more than 1 megabit per second. So it is not going to be a bottleneck. There's no bandwidth bottleneck on this. It's just fine. Okay. And in latencies, it's going to be within a data center, I'd imagine over here, no more than 100 milliseconds. I think over on this connection, no more than 100 milliseconds over here. It should be doing an end-to-end trip over here within half a second. And then this is a different story. Let's go ahead and any other questions before we wrap it up? I think we've probably tackled enough for this problem. Yeah. All right. Well, I'm happy with this. I'm going to post the diagrams in the pinned comment below the video. And then I'm also going to post the text file. I'm going to copy it into Pastebin and stick it in the pinned comment as well. If you guys can think of any questions after I end the recording, feel free to post them in the Discord or in the comments below the video. Thanks for watching. I hope you guys learned something or had fun with this problem. I will see you guys next time. Thanks. See ya.